2017.
All right, my name's Taylor Jacob, and I'm here to discuss a satellite-based IP protocol that I reverse engineered a couple years ago. This protocol is used all over North America to distribute news media, video on demand, films to movie theaters, digital signage, files, amongst other more mundane uses. There are many different protocols that operate on the same principles as what I will discuss today. I can't speak of the prevalence of these same systems or similar systems being used in Europe, but based on the vendor websites, I suspect there are similar systems used across the globe and not limited to just North and South America. So I need to start with a little bit of background to make sure we're all on the same page. Although there are many types of different satellites circling the Earth, this presentation deals specifically with the most commonly known type, geostationary satellites. These satellites are well suited for distributing a variety of information from a single source to a large geographic area. Most commonly known uses for TV content, but the setup is also well suited for the other types of media distribution. And there's typically no return path with this sort of delivery network, and that sort of setup is okay. If you're watching TV, it's not important that you tell the station you're watching, and if you're receiving media files, they generally won't be needed within seconds of delivery. Usually they position the data days beforehand. So for this, my hardware setup was pretty basic, just standard. I used some standard C-band dishes, which you see there, and a PCI DVB-S card, and just a Linux x86 PC. And for the software, I used all open source software. I used DVB Snoop, which is a transport stream analyzing tool, the regular DVB tools like SAP to tune DVB traffic, to do some in-depth analysis on the transport, or to look at the PIDs on the traffic, and then your standard Unix tools, grep, sort, unique, and other text-based tools. And then at some point I had to start writing my own software to get deeper into it. So before I dive in, I want to briefly cover some technical aspects of the satellite systems and the video formats. DVB is the most prevalent digital video broadcasting standard in the world. There's three main types. There's DVB-T for terrestrial, DVB-C for cable television, DVB-S for satellite. There are newer versions, DVB-S2, T2, and C2. And although the V in DVB would indicate that it's for video, it can also carry any other type of digital content. In the case of this presentation, specifically IP traffic. So the main difference between DVB, T, C, and S is the transmission medium. For T, it's the air. For C, it's a copper cable. And S, it's the Earth's atmosphere. The physical interface is generally referred to as a MUX in all three DVB flavors. In the case of DVB-S, it's also referred to rather erroneously as a transponder. And once the signals are demodulated into a bit stream, they're virtually identical. And the standard way this data is moved is MPEG transport stream, also called TS for short. Let's see. And the format's relatively simple. It's 188 byte packets that have a simple 4-byte header. And all you really need to know for this presentation is that it starts with 47 hex, and there's a 13-bit field called the packet identifier, more commonly known as the PID. So on the transport stream, there's 8,191 available PIDs, and of all of them, only a fraction will be used simultaneously. Each PID will carry a specific type of a traffic. It can be a single video stream, audio stream, program metadata, or other data traffic. The PRDs are how a set-top box or other component can filter out the content not relevant to their operation. For example, a digital video channel will be made up of a few PIDs. Generally, you will have one PID used for the video stream, another for the audio track, and potentially others for subtitles or captions or whatever you call it in Europe. That's what we call it in North America. So the set-top box would filter those specific PIDs and ignore everything else. And as far as encryption, DVB encryption will run on that 184-byte payload. It's just the generic 01 to B7 there in my diagram. So, and then the second part I need to cover is the packetized elementary stream and PSI data. PES is the format that defines how the elementary stream data, which is generally audio or video, is carried in a transport stream. The elementary stream is packetized in a sequential order, and the PS packets are sent on the PID. The format of the video or audio codec isn't defined, and it typically is changed over time. Historically, the video would have been MPEG-2, now it's H.264, and it's migrating to HEVC. And the important part, the important part that you need to know about this is packetized elementary stream always starts with that 001 sequence in hex. And the other type of payload, PSI, is most commonly described, is used to describe the layout of a transport stream, meaning how it's configured, what TV channels are available, what PIDs are available to find the video and audio streams on. But there's many other types of PSI data that allow different standards to ride on top of the transport stream to be able to define what is necessary for their application. Now, DVB multi-protocol encapsulation standard is a standard that pertains to this presentation. It defines the means to carry IP traffic over the transport stream. The key parts are one or more PIDs can carry DVB MPE traffic, and all the PIDs will operate independently of each other. Each PID's DVB MPE stream may contain more than one destination IP. The intention is to take the IP packets from one PID and put them on an Ethernet network somewhere once they're decoded. In North America, I encountered very little unencrypted unicast IP traffic, but I did see it here and there. The vast majority of the IP traffic I encountered is multicast UDP, since the satellite link is usually single directional. So a little bit of the background. I've always enjoyed scanning satellites for news events, feeds, sports events, etc. And although there's a lot of programming that's available for subscription, it's always been fun to see what you aren't supposed to see. When scanning signals with a satellite set-top box, you'll look for these hidden channels. It's common to run into lots that are encrypted. It's also common to find a transponder or transport stream that will be no programs on. And what you can see here is a set-top box doing a blind scan. And so anyway, so these transponders that have no programs, that aren't encrypted or anything, they obviously have some purpose, but it's not carrying television traffic. And many times they'll be satellite-based internet services, but not always. So for years I always wondered what they were, but I never did much investigation, assuming it was just encrypted internet traffic. But at some point, 7 or 8 years ago, I saw hints here and there on some forums that there being TV channels on these unknown transponders. They were calling it IPTV. Unfortunately, all these signals were on C-band, and I have a C-band dish at the time, so I set out to find a C-band dish and start examining these signals with a Linux PC. I've always had a PC around with a DVB-S card, so examining them was just a matter of sitting down and poking around once I managed to find a suitable dish and get it installed. So once I acquired my first C-band dish, I installed it and I started taking notes on these empty transponders. So the process that I would use to examine these empty transponders once I'd found them with the set-top box was to see what PIDs were present. Once I knew what PIDs were present, I'd start identifying them. At first I didn't really know what I was looking for, but if it was unencrypted and not a regular PES stream, I was interested. So one of the tools I used to identify what PIDs were present was DVB traffic. It's part of the standard Linux DVB tools. It operates by checking every packet in the transport stream over a second and counting what PIDs are present and the bandwidth. So you can see an output here. The capture on the right is from a regular TV mux, and you can see there's a lot of different PIDs and various bit rates. And the one on the left here is what I'm calling an empty mux that has one PID that has, you can see, almost 72 megabit of data just sitting there. So once I'd identified one of these PIDs with lots of traffic, I'd start to look at it in DVB Snoop. And DVB Snoop will allow you to examine in really fine detail whatever content is on a particular PID. So I'd use DVB traffic after I identified the PID. After a quick glance, you can see what kind of traffic is being carried. And yeah, if you look at this example here, I cut out a lot because it would have been 30 screens worth of data. But you can see that you can see it's IP traffic, and in red you can see the IP and the destination port. So I've definitely got some sort of UDP traffic here. So yeah, and a lot of this process, I'm mentioning it manually, but eventually I programmed it up because it was kind of boring to just write all this stuff on paper. So let's see. So anyway, DVB Snoop will provide a tremendous amount of detail about almost anything it encounters. And here's a portion of the output. Well, that's actually the portion of the output. So anyway, so basically, since it outputs text, I was able to pipe this stuff through grep and look at what IPs are present, and get other statistics and figure out what basically I was looking for. So, sorry, I'm a little lost here. So yeah, at first I wasn't really sure what I was looking for, but the first thing I did was to identify the IPs, the IP addresses that were present. Then I started looking at the traffic on each of the IPs. I realized very quickly that if I did encounter unicast traffic, it wasn't very interesting. Multicast was a completely different story. So looking at a UDP dump, looking at a dump of the UDP packets, you can see here that I've highlighted the 47s, which are spaced 188 bytes apart, and then in blue, which I guess you can't see very well, there's a bunch of the PES start sequences. So it's really obvious in this packet that there's some sort of video and there's some sort of transport stream, but how to get it out, I didn't really know at the time. So let's see. Yeah, by this point I reached the end. By this point, I had reached the end of the greppable part of my investigation, so I threw together some very basic code to capture the IP packets and manipulate them. At first, this little program just displayed what IPs were present on the PID. Then I started to save the payloads of certain IPs to a file, and I had my first results. The first success turned out to be linear TV channels. Linear is an industry standard term to describe real-time television station. These channels were made up of a single MPEG transport stream encapsulated in UDP packets with one channel per multicast IP. Each UDP packet would contain exactly 7 transport stream packets. Two transponders on the same satellite had a large line of encrypted channels, but a few more were in the clear. One of these happened to be NHL Center Ice. It stayed unencrypted for about 2 years. So to play these channels back on a computer, I wrote a simple program to capture the UDP packets and re-encapsulate them on a different multicast IP, which I would play back in VLC, which you can see a little screenshot here. So after finding the encapsulated linear video, I still had no clue what the majority of the multicast IPs were. There was one multicast IP on the same transponder as NHL Center Ice that took up most of the bandwidth of the transponder. So I'd learned from the linear video that each multicast IP was used for a single program. If you used the same technique of saving the UDP packets to a payload on the unknown IP and tried to play them back, every now and then VLC would attempt to render a picture or start to play a short sample of audio. And you can see an example here of how it would kind of start to render something, but you wouldn't really get anything. And I found examples of this type of behavior on numerous satellites. If you examine the UDP payloads, you'd see all the telltale signs of the MPEG transport stream and PS packets, but I couldn't figure out how to extract them. So upon closer examination, it was clear the UDP payloads had some sort of header on them, so I wrote some software to strip some number of bytes and save the UDP payload. Using the same grep technique, it wasn't difficult to determine what was the header and what was the payload. I tried this blind header stripping technique on numerous transponders without much luck until I tried it on a KU transponder that I had tucked away in my notes. On this transponder, I got lucky and managed to get some playable video. Although I was excited to finally get video that would play without error, it turned out to be an episode of Dr. Oz. American daytime program wasn't exactly the most rewarding prize, but it was progress nonetheless. Still wasn't sure why my other previous attempts at header stripping had not worked yet on the other transponders. So by this point, I determined the header and the packets were a fixed size with a few exceptions. I started looking at the header more specifically to see if I could understand why I had not always been able to get some sort of video to play. Much like before, I used DVB Snoop and grep to examine just the UDP packet headers in real time. And looking at the slide, you can see almost immediately that the headers have some sort of 32-bit field that is interleaved in red, interleaved, and a separate 32-bit counter in blue as the number the number would increment in each packet. I don't know if you guys can see the blue that well, but anyway. So I started to look at the different transponders in my notes, and I realized that I wasn't dealing with the same protocol, or at least the same version of the protocol. And I identified at least 5 different systems that are all almost identical in design, very similar on a technical level, but different nonetheless. I started to focus my efforts on the high bandwidth C-band transponder that carried NHL Center Ice, as I thought it might yield the most interesting results. From here on out, I mainly focused my effort on this transponder and the unknown protocol it was using. So going back to the slide, you can see almost all the packets start with 2 bytes 0 and 0 1. And I started to speculate that the interleaved 32-bit field on the header was some sort of transmission ID. So I wrote some test code to start saving each transmission ID to a unique file. And with this basic change, I was able to render video from a much larger percentage of the files, and it became clear why my header stripping previously was so hit or miss, was that multiple videos were being sent at the same time. So I examined the files that I couldn't play, and I looked at the packet headers for clues. Almost all the transmissions are sent in a sequential order based on that counter, but in the examples I couldn't play, the counter wasn't in sequential order. So I realized that the counter was actually a block number in the transfer and started saving the payload using the counter as a block, saving the payload using the counter as a block as an offset. This cleaned up almost all the errors I was getting, and I was able to play back almost every file. So once I was able to play the majority of the files being transferred, I also noticed the running time of the videos were significantly longer than the time it took to download. It was only then that I realized the files were meant for playback in the future, i.e. a content delivery system. So being able to save the media files was a great achievement, but it left a lot to be desired. Every file was saved as a 32-bit number, and the only indication as to what content was required further examination, which usually was me trying to play the file in a media player. So I'd also received the files numerous times. I had no knowledge that it was a retransmission. I also noticed for the first time at the end of these files, the end of these files always contained some seemingly random data. I had a hunch it was some sort of error correction data, but I had no way of proving it at the time. Seeing the split between the file and this extra data was pretty obvious. The random data always started on a packet boundary. So I knew there were other packets in the stream that I was ignoring, and I assumed they had to have some sort of control packets. The receiving stations had to be aware of the files, know when the transmission started or ended. I started logging all of the non-payload packets to a file. It didn't take very long to get a basic understanding of the other types. All the packets had the same 8-byte header, at a 16-bit packet type, a 16-bit packet length, and the 32-bit object field. After this, all the packets differed. But since all the packets used the same object ID field, I started to look at how other packets correlated with the file I downloaded and see what I could determine. The 03 was the most prevalent packet, and it was the longest of all of them. At a quick glance, you could see ASCII strings containing what seemed to be quite obviously file names. I'll come back to this in a minute. The other two packets were the 06 and the FF, and they only occurred before and after a transmission. Their bodies were really short, and it was soon clear that they were used to indicate when a new object ID was starting in the stream or when it was being removed. So the 03 packet, like I said, I'd come back to. This is the one I was looking for. It clearly contained the file name along with some other descriptive information about the file. So I started logging as many of these as I could and looking for patterns. The process I used was pretty rudimentary. I used Vim and looked at packets side by side. I piped and grepped packets with various filters to see what pattern I could discern. The first problem was the location of the ASCII file name was not at a fixed offset into the packet. This meant I had to look more into how the packet was structured to be able to programmatically extract the file name. So my goal was to try to identify as many parts of the 03 packet as possible so that I could see what remained. I assumed the packet was made up of little endian 32-bit and null terminated strings since there were a lot of zeros. I knew the total payload size, including the extra data. I had a good idea of the file size with a few hundred bytes when the extra data was removed. I also knew the transmission block size. I was able to clearly see the file name in the packet as well. So I found a date field that was usually within the past week or so in Unix timestamp format. So I may be showing my age, here a little bit, but I printed out hex dumps of a couple of 03 packets for all these properties. I may be showing my age, but I printed out hex dumps of a couple of 03 packets for files I knew all these properties of and highlighted them. So once I'd marked off all these areas, it was obvious that the fields I was interested in were all clustered together. You may not be able to see it clearly here in the photo, but there was always a 32-bit little endian 02 right above the transmission block size, which is highlighted in yellow on there. It was followed by a 32-bit little endian length that correlated with 13 bytes after the file name, which was usually the end of the packet. Based on this knowledge and a little bit more human pattern recognition, I was able to make a parser that was token-based starting 24 bytes into the packet. Now, this had some major flaws, and it would crash fairly often, as I didn't know nearly enough about the format. But regardless, I was able to properly save the files with the correct file names. I added some balance checking to my parser to stop segfaulting, and I logged the errors. And whenever I would misparse an 03 packet, I would compare the packet that crashed to what I was expecting. And this process continued on and off for a year or two until the parser stopped running into errors. I'm sure my parser routine isn't a facsimile of the real software, but it's been stable for 4 to 5 years now. So the two big problems at this point were dealing with the volume and the speed of the transmissions. The big video on demand system had 2 transponders that combined were a constant 150 megabit stream. I could fill up a 2 terabyte hard drive in less than 2 days. And most of the content I was collecting, I had little or no interest in watching, but I was able to filter out some of the content based on file names. It wasn't an ideal solution and required me to manually clean up the hard drives every few days. But over the course of a month, I set up a 10 terabyte array of 2 terabyte drives. I never fully addressed the volume of the file problem programmatically, but with some string matching, I was able to reject a large enough portion I could sort through the files once a month or so. The overall bit rate was the most difficult problem to tackle. This is by far the most IO-bound application I'd ever worked with. The transmissions were constant, so I needed to be able to write data at least as fast as the bit rate because no amount of buffering would help. The 10 terabyte array was more than adequate to keep up with the data rate if I totally left it alone, but when doing other operations on the disk, I would run into problems. So the first thing I tried to deal with was to increase the buffering on the DVB driver. I tried using a buffer as big as 64 megabytes, but that only covered about 7 seconds. The value I'd been using before was 4 to 8 megs, so it was an improvement, but it alone didn't eliminate the problem. I can't quantitatively say how much it helped, but I still ran into problems very consistently. So from watching the hard drive light, it was clear the data that was being written to disks in quick bursts of a second and then a pause for a few seconds. I started to look at the disk using VMstat, and you could also see the burstiness. And you can see that here in the slide on the top, the blocks out field there in red. You can see it's writing nothing and then writing 45,144 and then nothing. And well, I'll explain in a second. So I did some research and found the kernel settings to control how much inode data is cached in memory until it's flushed to disk. There's a pair of settings in the kernel, VM dirty background bytes and VM dirty background ratio. And what these settings what this setting does is either it sets a byte limit or a ratio to the amount of data being held in inode cache before flushing it to disk. The box I was using had 8 gigs of RAM. The default setting for the kernel I was using was 10%. This box wasn't using that much RAM for applications. To be conservative, 4 gigs were being used in inode cache. If 4 gigs were being used for inode caching, a write wouldn't get flushed to disk until approximately 400 megs needed to be flushed. At 150 megabytes, a rough estimate would take around 20 seconds to add 400 megs to the buffer. The problem was the buffers would still be filling while the data was written out, so that's why the bursts were so much closely spaced. The real problem can be seen in the upper VMstats WA field. This is the percentage of time that the IO operations are suspended and where buffer underruns could occur if everything in my application had to stop and wait. So basically that means that everything's waiting for that IO to happen. So that last row right there with the yellow, so 17% of that 1 second, everything is just paused. So to stop this behavior, I changed the VM dirty background ratio bytes to 0, which meant that the data was written to disk as soon as it expired. This immediately changed the disk access behavior to be much smoother, and data was written out as it was received continuously instead of being so bursty. It also meant the potential spikes in IO blocking were reduced significantly. So you can see this improvement in the lower VM stat output, and you can just see it's like writing a consistent 8,000 in each sample. So after tweaking the VM dirty settings, my client was able to write data reasonably well, but I still ran into problems doing other file system manipulations and very specifically deleting a file. Up until this point, I was just using the ext4 file system that is the default with Linux. I never had any reason to use anything else as it met my needs. I started researching file deletion times, and the larger a file is in the ext4, the longer it would take to delete due to inodes being fragmented. I did some work on MythTV years before, and I remember the hardcore users recommended something other than ext4, but I couldn't remember why. It turns out that the long deletion times were causing the IO. It turns out it was long deletion times causing IO issues. Did a little bit more research, and I started trying various file systems. I ended up settling on XFS. Two main reasons were that you can control how large a block of the disk was allocated at a time, and the file deletion time was always fractions of a second, regardless of how large the file was. The large block allocation was also very useful, since almost every file downloaded was multiple gigs. I set that value to 1 gig. And there's some XFS tools to see how many non-contiguous blocks a file takes up, and with the 1 gig setting, even for really large files in the order of 20 gigs or more, they'd still be split up into a few pieces. So by this point, I was able to store just about every media file from the video-on-demand distribution system, but I still had problems here and there due to reception problems. But overall, I was able to complete 95% or more of the files, and buffer overruns due to I/O were a thing of the past. So, although I was quite pleased with being able to store and organize the files due to the nature of satellite transmission, I would quite regularly be missing a few packets from transmissions. It was quite frustrating to be missing 1 to 2 packets from a 20 gig movie. So eventually I decided that I should take a look at the FEC. Up until that point, I didn't understand much about FEC aside from that at a high level it provided data protections using some fancy math I didn't understand. At some point, I found the vendor's website and it mentioned using a proprietary FEC method. So I started to do some research into FEC, and I started looking at the files I was downloading for any clues on how I could use to focus my energy. I knew the FEC data always fit exactly into the packets, and I knew there was no padding. There's no padding on the FEC data like there was on the actual file. So this led me to believe that it was block-based. I also noticed the ratio of FEC data had a close correlation to the file being transmitted. I started examining other systems that used the same protocol. I noticed this ratio differed a little on different systems. C-band tended to use less redundancy than KU. This most likely is because C-band is less sensitive to interference and signal loss than KU band. So one of the more important observations that I happened to notice is a single packet transmission's FEC was an exact copy of the payload. So this slide's an example of a 2-packet file that was 2,600 total bytes. You can see the contents are the same at byte 0 and at byte 1300. And up until this point, I was mostly overwhelmed with attempting to know where to start because I'd focused my energy on the large files for some reason. So I started examining the smaller transmissions and started collecting samples of 2, 3, and 4 packet transfers. At some point during my research, I'd done patent searches and come across some potentially useful FEC schemes, but hadn't been able to make sense of them. I eventually went back to these patent documents and started trying to piece together how it had all worked. It was this mundane patent search that actually proved to be the breakthrough I needed. I just didn't know. The answer was sitting under my nose the whole time. So from this point on, I started researching all the math mentioned in the patents and trying to remember how matrix math worked. I had to learn all about finite field math, Galois fields, and matrix math. Over the course of a few weeks and many sheets of paper, I managed to calculate the FEC of a small file examples by hand. I don't want to turn this into a long math lesson, but I want to walk through the high-level overview of how the math works for the FEC system. So a key part of the forward error correction is Galois field arithmetic. A Galois field has 2 important properties. The first is that it's a set of integers that math operations, addition, subtraction, multiplication, or division between the integers are another integer in the set. The second property is that the field is finite. The FEC scheme that I'm speaking of, and in fact most others, are a set of algebraic equations that are used to calculate the missing elements from the other. So performing the math operations in a Galois field are different than standard math. Addition and subtraction are just XOR. Multiplication and division are a bit more complicated, but the total possibilities for a 2 to the 8th field are small and can easily be performed in a computer with a lookup table. All Galois field math is done using a primitive polynomial, not reducible by any other polynomial. In the case of the 2 to the 8 Galois field, the polynomial is represented by, it's represented by the x to the 8th equation there on the bottom. So this is the same polynomial used for QR codes, Reed-Solomon, and lots of other error correction schemes. So the FEC method I employed, I found out later, was called the Vandermonde FEC method. It consists of the basic equation y to the k equals x sub n times g, where y to the k are the transmitted code words. Those are all the packets with the FEC data. X to the n is the original data, and g is this n by k generator matrix. And you can get back x to the n with the following equation, which is x to the n equals z to the n times a to the minus 1, which is your repair matrix. So yeah, so the second equation, z to n is where you received code words, and a to 1 is the repair matrix it's based on your generator matrix. You have to have at least n elements of z to be able to recreate x. So the whole principle of the FEC system is you have a system of k equations and n variables. So if you have at least n pieces, you can solve for the missing values. So what does all that mean in a real-world implementation? Well, let's roll up our sleeves and do some matrix math. For example, I'll do a demonstration on a 2x3 FEC scheme. This means there are 2 bytes that we want to protect using 3 bytes. It's a small enough example we can do it quickly, and yet the whole process will be understood. So the first step is to build a generator matrix, and for this example, it'll be 2x3. It'll be a 2x3 van der Maan matrix, and this is the equation right here. And basically, it's just a simple geometric progression. So the 2x3 van der Maan matrix for the Galloway field 2 to the 8th is figure 5, but this isn't the generator matrix. To create the generator matrix, we need to get it to standard form by reducing it. I'm not going to get into this, but that's what figure 6 is right there. And you'll notice the 2x2 part on the left of the matrix is all ones in the diagonal space. This is called the identity matrix, and it'll also prove very useful features later on in the FEC scheme. Okay, so for the 2 bytes that we want to protect, they're 1F and F7, and I got these values from actual packets, and you can see that in figure 9 here. So now to do the math, I don't know how many of you remember how to do matrix multiplication, but I'd completely forgotten. In a quick review, you flip the 2x1 matrix on its side and leave the 2x3 matrix alone. You multiply the 2x1 matrix on the left with each row and end up with a 3x1 matrix. So to do the math, you multiply 1f by 1 and f7 by 0, and you follow this through for each of the three fields. So in a Galloway field, anything times 1 is itself, and anything times 0 is 0, so that makes 3 of these easy to see. The first byte of the code word is 1F, and the second is F7. The last field I'll give you some help. 1F times 3 in the Galloway field is 21. F7 times 2 is F3. And 21 XOR to F3 is D2. So D2 is the FEC value, which would be in the third packet. That would be the byte transmitted in the third packet. You'll also notice the great property is the first 2 bytes of the code word in the original form are the same. That's because the left section is always the identity matrix, as I mentioned earlier. This is the case for any FEC data rates. It also means that all the bytes that are written to disk for a transfer won't have to be altered later. So now that we've been able to generate the FEC, the next question is how do we get the data back out? So let's say in our example from before that we get the first packet and the third packet, and we've lost the second. Since we got 2 packets of the code words, we'll be able to generate the missing byte from the second packet. To do so, we need to build the repair matrix. Now, to do this, we take rows from the generator matrix for the packet, and we build a 2x2 matrix. In this case, it'll be what you see here in figure 13. The 1 and the 0 correlates to the first packet, and the 3 and 2 are the the generator matrix's third field. So the matrix needs to be inverted to create the repair matrix, and I'm going to spare you that trouble, and that's figure 14 there. So this gives us A inverse, which is what we use to generate X sub n. So now we multiply the 2 bytes that we have, 1FD2 by A inverse. Now the math is the same as before, basic matrix arithmetic. Now it's a very simple example, but that explains the process. I did numerous examples on paper before I was able to understand it enough to do much in software. So now that I understood how the FEC process worked, I started to work on a software implementation. Luckily, since Galloway field math is very standard in computer science, it didn't take long to find some code online to build multiplication and division tables. Once I did that, I wrote software. I wrote a few functions to reduce and invert the matrices. By this point, I had all the mathematical tools and software and needed to weave it together to be able to do the FEC. So for this part, I modified my software to stop truncating the FEC data out of the files when I saved them. I collected a few examples of complete files with complete FEC repair sections. And since I should be able to generate the FEC sections as well as repair sections, my first step was to write software that would verify the FEC data fields in the saved files. Didn't take very long to implement this in software for files that consisted of less than 100 packets, but after that I ran into problems with files that consisted of 101 packets. I made the assumption that 100 must not be some arbitrary limit, and the programmers had decided on it for some reason. It turns out that after 100 packets, the packets are interleaved, so that 100 by x is the largest scheme. The interleaved data rate was easy to calculate based on the total number of packets divided by 100. And any packets that weren't present to get to the even 100 were just considered all zero. So all of these little things necessary to do a complete implementation were easy to test in software with complete file and FEC sections to test against. So by now I was elated that I was able to repair bad files, but I was still not totally sure what the FEC rate would be. I could make some assumptions based on the total file sizes, but I took a look back at the myriad of unknown sections in the O3 packets from much earlier, and sure enough there was a field that correlated the FEC and data rate. It was a 32-bit field after the file name. The only reason that I wasn't obvious was it was stored as the FEC value times 100. So if the FEC scheme was 100 by 106, the field would be 10,600. So once I had this last piece of information out, it was time to try and do it. It was time to try and do it in a real time on the live stream. So the time it takes to build the generator matrix, which is the basis of the repair matrices, is quite quick for the 2x3 example I just presented. But with the larger FEC rates that are used in a field such as 100 by, in such as a repair as 100 by 109, takes much longer. So I pre-calculated the generator matrices, and I stored these in a header file that was compiled into the executable. I only stored the section of the generator matrix used to the right of the identity matrix. And once I implemented the FEC, I was able to emulate as far as I could to the entire protocol. So if I ran into any I/O errors, the FEC was able to repair these in short bursts. So in conclusion, the biggest challenge of the project for me was the FEC, as the math was something I never really dealt with in my schooling, aside from remembering it long enough to pass a test, and that was it. So I'm sure you'll be wondering about the video on demand system if it's still running. The system is running, but all the files now are encrypted and using some sort of scheme based on AES 256. So hopefully I've explained all this in a way that's easy to understand, and thank you for listening to my presentation.
So once you'd applied all the error correcting stuff, what proportion of the data stream were you able to decode successfully?
100%.